Thank you, Helmut. Thank you, Isabella, for being here today. Please give them a welcoming applause. And then I hand over this mic to you.
Thank you very much. So, welcome to our talk. Thanks for having us. Today, we want to talk about entity component systems and give you some insights on how you can create your own one or come up with your way of creating it or having your data layouts and architectures that you want to have. So who are we? I'm professor for computer science and Isabella is my student. Our third speaker cannot make it today. Unfortunately, I will take over for her. We are from the University of Vienna, even though I have my PhD from this university. I've been into C++ since the early 1990s, so it's quite a long time now. I programmed my master thesis with C++ already. And I do teach courses mainly in the area of games and entertainment computing. And this semester I will have a talk, a lecture about gaming technologies. It will be about AI, physics, parallel computation, multi-threading data. And what I will bring here will be also part of this lecture. Other lectures include real-time computer graphics, mainly focusing on the Vulkan APIs. I've been teaching the Vulkan API now for 8 years. And my research interests are video game related. On the one hand, it's about storytelling and engagement. On the other hand, it's really about technology, mostly, of course, using C++, and a lot of AI, of course, these days. I create my own projects on GitHub. Over the years, a lot of them have been created. And I just want to mention why. First of all, yes, I love to program C++. Guilty. I've been doing this for so many years. And okay, the pointer doesn't work. Okay, it doesn't matter. Of course, what's more about it, by doing it myself or with my students, I really learn a lot. So, all about the nitty-gritty details, about the choices, about data structures, about modern C++. So I throw as much modern C++ into the project as possible. Mrs. Hölzl knows what I'm talking about. And of course, it's a good teaching resource. So we can have a lot of bachelor's and master's theses and students working on either extending the libraries, optimizing them, creating new stuff. It's not intended to be production code in the kind of it's never really finished. It's all an ongoing thing. Speaking about modern game requirements, in modern games, depending on, of course, the game genres, you might have even thousands, hundreds of thousands of entities, bullets, particles, items, world environments, dust, debris, non-player characters that all are behaving in a kind of a dynamic way. So their behavior adapts to the situation of the game, of the input of the player. We have a lot of AI these days. And in order to cope with that in real time, because we're talking about real time, we have to be very efficient. We have to use the memory efficiently. We have to be cache friendly. And to optimize all the computations. So we need a lot of data-driven design. We need a lot of cache-friendliness design. We need to make use of the multiprocessing capabilities of modern CPUs. And basically, we are also faced with a lot of interactions between different parts of the game that have to work together. So this is a very simplified, of course, sketch of a game loop, of what a game does. So, of course, games will hardly look exactly like that. It's just to make a point that when you run a game, usually you're running a game loop, and inside the game loop, then you would have to go to do a lot of tasks. Some of them you can do in parallel, some of them you have to do in sequence. You have to process user input, you have to update networking if you're on a multiplayer game. You have to update your physical world and advance the simulation of the physical world. You have to update your AI and make new decisions for your NPCs. And finally, when you're done, you render the next frame. Hopefully you can do a lot of stuff in parallel, and then you repeat, rinse and repeat. So this is how a game looks like. if we come up with stuff that is inside a game, we might call them game entities, and of course we can apply object-oriented design in order to come up with our game object class hierarchy, and that would be an example for that. So we might have, as a most basic base class, we might have like an abstract game object, and then we can have any type of game object derived from that, about like an item or a character or an environment. But a character can be, of course, a lot of different characters and represent a lot of different characters. So you might have a player, for instance, is a character, or you might have an enemy that is a character, or you might have some NPC that's running along. It's neither the player nor an enemy. Then you go to the enemy and you find out that there are many different ways that NPCs can be enemies. So you might have a flying enemy, you might have a shooting enemy. You might have an enemy running on the ground, or a spellcasting enemy. And then it gets really funny, because then you might have combinations of that. So you might have a flying shooting enemy, you might have a ground shooting enemy, you might have a flying spellcasting enemy. And if you really want to have this in a class hierarchy, then you have a bit of a problem, because you have a lot of combinatorial explosions. Where do you really want to put your code? Should it be inside of these derived leaf classes, or do it have to bubble up sometimes? You might also have this diamond of death, where you have to inherit from multiple parents. So for game objects, it turns out that having this kind of characterization and class hierarchy is not really optimal. So object-oriented design for game objects, we have rigid hierarchies, the diamond of death, we have combinatorial explosion. Even though we want to have separation of concern, so we want a flying enemy just to focus on flying, and a spellcasting enemy just to do spellcasting. But then we have all these kind of combinations, and if we put this into an array like that, where we create all of our game objects, and then we might call a virtual function update, then of course, because all of these objects are completely different, we will call a lot of different virtual functions, and we will hop around in main memory, and that's not very cache friendly. So we were using virtual functions in a bad way here. So what's the solution? The solution is to have combinations of components, and entities are actually made of these single components. So we want to combine stuff and characterize our enemies by the components that they have. So here in this example, our entity 1 would be a flying enemy entity, and entity 101 would be a flying shooting enemy. And the difference simply is that the flying shooting enemy has one more component. And the components are separated from each other. It's just a struct or just a plain old data. And that's why you can actually recombine all these components, and the outcome is then exactly what you want. And that gives us an entity component system, or ECS. So in an ECS, we have these three pillars. We have entities, which are like the abstract container for all of these components. Usually you would identify them by some unique ID. It can be just a number, just an integer. It can be even a handle that is composed of different parts. A more intelligent number that has different parts. And then you have all of these components, and usually they are like pure data, POD, and there is no specific behavior attached to a component. It's just data. It's just there to linger in memory and do nothing. Of course, you can put some classes also in the ECS but that is something that you actually should avoid, at least for games. So, for instance, we could have as components position, velocity, mass, acceleration, moment of inertia, all of these things that characterize our game objects. And finally, we need some logic that is operating on the components, and that's called a system. So a system can be as simple as simply a function, a very small function. We will see then an example for that. And that's the logic that is operating on entities. And you can have many systems. You can have hundreds of systems if you want. And all of them must be started at some point, and then they will select components, and then usually they will operate on these components. Maybe they will iterate over a specific combination of components from top to bottom, and that makes it very, very efficient. So the key principle here is the composition rather than inheritance. So what are typical ECS operations? Obviously, creating new entities, and when you create it, you get a handle or an ID back. You might add components to the entity. You might erase components from the entity. You might read or change component values. You might erase whole entities. And then, very important, you might want to iterate over entity groups. And that means you want to identify entities, for instance, that have specific component types. So we will see that later on. In a physics system, you're interested in position, velocity, and acceleration. And a group of entities for a physics system would be all of the entities that have these three components. This is our group. Now we want to iterate over all of them in a range-based for loop, for instance. And then we can make an Euler step, for instance. So here, as an example, an AI system might iterate over all entities that have a position, velocity, and have a tag intelligent. So tags are also a way to furthermore enable grouping. So it's like a label that you put on entities. It's not really data. And when you create a view, so when you try to make this group where you want to iterate over, you might say, I want to iterate over all entities that have position, velocity, and have this tag, but they don't have this tag. Okay, so that allows you a very, very good grouping. So here, this is from my own ECS that I've implemented last winter semester because I had a lot of time at my hand. So this is how it looks like. So here we would have the register, which is simply the container of the world, and a handle would be something that identifies an entity. And right off the bat, there is nothing in the handle. The handle is empty, and I can test this, that the handle is not valid because it has not been used yet. And here and then I can insert something into the world. In this case, it's just a string that I put in. So the entity that is created will have only a string, and I get the handle back. And then the handle will identify this entity that has just been created. And I can ask, does it exist? And yes, hopefully it has been done. I can insert more than that. So here I insert an integer and a float. And then I can just test whether, for instance, this entity that is represented by the handle actually has an integer component. And then we can go on. We can call something like get. So that's the main name. And get the integer component from this entity. And then the value is copied in this case. And I have the value in my local variable. I can also erase an entity. And then I can check that it no longer exists. Now, looking at this, we see that we can identify components by their type. And that also means that components cannot have the same type. So if they are attached to an entity, they must have different types. So what I cannot do is do something like this. Insert 5 and 6. These are both integers. That will not work. So I can put them into a struct, for instance, give them some naming, which makes a lot of sense. So I put them into this wrapper, and then I can put them into the, I can insert the entity, and I have my new entity with the height and the weight. But as I said, with different types. So components are unordered. They don't have like a number. Usually it's like a set. You're either in the set or not in the set. It's not like in a tuple. In a tuple, all the components have their own index. And because of that, we need the types to identify the components, and therefore types must be unique. And I have to enforce that somehow. And I will show this later on, how I do it. Also, if you want to insert stuff that has the same type, you have to put it into wrappers. I do use my own strong type. I have created this also. It's not only a wrapper, it's also for convenience. I can partition bits and have access to them. And also, I use my own phantom type. And that's very nice because here we can see how to use that. If I create a new type size, T for instance, and make it a strong type, then without the phantom type, these two will be the same because it's just an alias. But if you add some unique struct or unique type here, which is called a phantom type, then these are indeed different types. And now you might have to come up with struct number 1, struct number 2, struct number 3, but having this type-based counter is very, very nice because you don't have to do that. It's a type-based counter. If you're interested in that, I lifted it from a talk that was given. And it will also always come with a new number, and therefore you get unique types. So what's a system? The system is a unit of processing. Usually it's functions or classes. You're responsible for a specific task. You really want separation of concern here. They do not store usually state information. Well, you can have some kind of system-related state information, but instead they operate on the component data. So they run through all of component combinations. So typically they iterate over specific component combinations. Here we have a couple of examples in a game. So, and here a rigid body physics system running every single frame iterates over all entities that have the components, position, orientation, velocity, mass, inertia tensor, and they have the tag dynamic. And so you have like a subgroup because other entities that don't have the tag dynamic, maybe they are static, they are not allowed to move at this time point, or they're not taking, they should be invisible to the physics system at this time point. So it's good to have some kind of tag mechanism to really put labels on the entities also. So that would be a system. So how does it work in my own entity component system? This would be a system. It's just a function, update. We give it the delta t, so the time we had from between now and the last update might be like 10 milliseconds or so. And that means that I have to advance my physical world by delta t, by this 10 milliseconds. And in order to do that, I ask the world, give me a view which collects all the information you need. It finds all the entities that have these types of types. And we can also see that some of them don't have references, some are references, and that means that I can actually change that. This is just copied, and this is really a reference then to the component. And then I have my range-based for loop and my structured binding run through the view and update velocity and position. This is actually a symplectic Euler because we update the velocity first and then use the velocity to update the position, the new velocity, which is a more stable version of an Euler. So, of course, there are other entity component systems, very good ones. This is one of them, NTT. They are very much the same. If you look at the source code, you create an entity, you get a handle back, you can destroy the entity, you can test whether the entity is valid, you can create position and velocity, as part of the entity, as components. You can test whether there is this component, whether an entity has a component. You can get the position. You can remove a component. And finally, of course, just like with my own, you can create the view and then use that in a range-based for loop, go through that, and then get all of these. In this case, what you get is the entity, and then you go through the entities, and then you say, okay, get me all of these components from the entity. In my ECS, I get the components immediately, so there is not this step of going through all the entities. Doesn't mean that mine is better. We will see that it's actually not, but it's just a different view. So if you want to use an ECS in your project, choose in this order. Use an existing battle-tested one. So any one of them, Entity, Flex, Pico, they're very good, very fast. Flex is incredible. You can create your own with an LLM, and that's interestingly very easy. Just type in create me an ICS. That's all it takes, because it's just a standard structure, and you'll get a different one anytime you do that. Sometimes you might not be satisfied with what you get, then you have to kind of put in more specifications. You might also create a simple one yourself, but only if you have really, really, really a lot of time, and you need something very special. Then create your own ones. Okay, so that's my take on that. So here is an example. Claude AI, create a simple C++ ECS with templates. This is what comes out. It works. It's not the best ECS, but it works, and that's amazing. And it's like the pure, the necessary thing you would expect from an ECS, but of course not more. It's very, because it's a simple ECS. I ask him to do that. And here I use what is used is an unordered map with a specific type name T, and it maps the handle or an ID, which is simply a size, to the value. And that means that for every specific type, I have my own unordered map. And all of the values of a specific type are stored inside of this map. So that's really a very simple solution. It works right off the bat. It might not have the best performance, but I would really recommend to start with something like this before getting into the details. If you want to have more performance, you need to view the whole thing from the usual way of thinking data-oriented. In an ECS, data-oriented design is preferred to object-oriented. So we think of the data layout first. How can we optimize that? How can we optimize accesses to that? Because we want to be as fast as possible, obviously. And then we design the operations for reading and writing the data. So which data layout to choose from? There is a gazillion different choices. I want to present a couple of them. And all of them are actually a kind of compromise. So none of them is really the best one, unless you really spend a lot of time in optimization. If you're not willing to do that, there will be some compromise. The biggest question you have to ask yourself, is performance important? So like with a game, if it's not so important, then just create your own with an LLM. If it is important, then the question is, which operations should be optimized? Should it be optimized for throughput, or should it be optimized for latency? How should I organize my data? How could I make it cache friendly? Number of levels of indirection, of course, that might have an impact on the latency, for instance, and the order of so how many operations are needed for creation, lookups, change of components, and so on. In video games, we have a hard limit on the frame time. Typically, it's 1/16 of a second or less. And we run through large lists of component combinations sequentially. So this is one use case from top to bottom. So in this case, we want to optimize for throughput, and it should be cache friendly. So the data should be the data access should be predictable. But of course, a system might also access single components, and then we should optimize for latency. We want O1 access, and we want to limit the number of levels of indirections to keep that also at bay. So we have a couple of choices. We could actually put all of our game objects, or all of our components, into a map, which results in a kind of a balanced tree. This is an interesting stuff. So we could also have an unordered map. Of course, all of this is scattered in main memory. In an unordered map, data accesses might be a little bit better. We will have to look at it. But still, if you have hash collisions, then you might have more memory accesses, and that's not so good. Or you put stuff into an array, like a stat vector or some other array, and when you go from top to bottom, then of course we are cache optimal, because then we can prefetch all the data from main memory, and we are much, much more efficient. When we do that, obviously what we do is we don't store data in a huge array, like in megabytes, because the operating system might not be able to yield that. What we use are these segmented vectors, where we have segments of arrays, and then the components are stored there, and then you have like a lookup table, when you look up, so this should be, of course, powers of 2, and when you look up like the hundreds of them, then you can just do a bit shift. You get the entry in this lookup table, and then that gives you a pointer to the segment, and then you go into the segment and find the value. So that is something that is used, and that allows you to be very efficient about your memory. Now, we might use something like this. So this could be an array with our components. And in order to find the right component, we have an unordered map that maps our handle to a pointer, and the pointer might then point to one of these components. That is totally feasible. And so what's the benefit? The benefit is, in an unordered map, on average, I have O1. But when I want to go through all of these components of a specific type, then we are cache optimal. So again, right off the bat, we have found something that might be interesting. But what about if we want to go over more components, like game object, character, enemy? Then what we can do is we have to run through the unordered map, because that's a key value pair. We get not only the pointer here, but also the key. We still run through this like this, but of course other instances for other types might be ordered completely different, and that means that I take the handle, go to this map, and then land here. So with the first run, with the first one, we might go through that, but here we're jumping around in memory. This is something that has been quite new. I think it's C++23, a flat map, and the flat map is organized like this. So we have the components laid out in an array, and here we have the keys to that, and the keys are ordered. So that's very nice. If I go from top to bottom, I immediately have my keys, and I can use the keys to find the other component from this very entity. The problem is that the keys are ordered, and that's not good. So inserting something can have an order of like n, and that's not what you want. That's like the worst case you can talk about. Finally, this is a data layout that makes a lot of sense. You have a linear layout of your game objects and components. And together you have also the handle. And if you want to go through all objects that have a game object and a character, for instance, you can go from top to bottom, look up the handle, and then find the component in the other. Again, this would be cache optimal, but when we access other components, then we are jumping around in main memory again. So cache efficiency is actually very, very important, and the data should be stored in a contiguous way, but also dense. What we don't want are any gaps here, and that means that if I erase something, I have to close the gap. I have to make a move operation, and that is something that's not desirable. So it brings a lot of problems. So, but is it really so much better? So I had if it is contiguous and if it's cache friendly. So I ran a couple of experiments, and here we have two lines. When we for each of the x-axis values, this is a number of reads. So I have a segmented vector. Segment size is 1024. I have 32 bytes of reads that I do, and I fill up the vector with random numbers. And then I have two modes of running through that. One would be completely sequential, so going from top to bottom through the segmented vector, and then take the time it takes in order to make like 10,000 reads. And this would be jumping around randomly. So we're not going from top to bottom, we're just using the random number also to make another random index, and we immediately see that random jumping around indeed is much worse than when it is cache friendly. It doesn't get better if we go to the case where we are here. So the other lines are, for the first component we go from top to bottom, then we take the handle, and then we have a random read. Okay, so these are the other lines. They're also called random, but it also always means that the first component is run through sequentially, but then I want to make reads from 1 component, 4 components, 6 components, 8 components, 10 components. But the first component is always done sequentially, and the other ones are in random order. Now, I can have a look at the different properties of what I've just said. So we have flat maps, we have unordered maps. We have unordered maps with a dense layout, and they all have problems. So flat map, right off the bat, inserting and erasing is not very good. Unordered maps, on average, it's 1, but it can, in some cases, be problematic. You have too many hash collisions. And then we have something like this. This seems like the holy grail. We have O1 access, we have good cache performance, and here we have, if we access only one component, this is one component access, but we iterate over n components, and that looks the best, and that's using slot maps and archetypes. So what's a slot map? A slot map is a map with a lot of slots. So this is an array of slots, and a handle is used as an index into this array. A handle actually doesn't have only an index, but also a version number. So that's very important. And in the slot map, we also have an index and a version number. So if I want to access an entity, in this case, I take this handle and I say, okay, the index is 0. So let's look into index 0 here. And then we match the version numbers. And only if the version numbers match, I know that the handle is actually valid. because you might have a stale handle. You might point to an entity that's no longer here, that has been destroyed. And by using this versioning, you can actually prevent that from happening. You can detect it. And then you have some kind of way of saying, okay, here in the slot map, then you have some way of finding then the actual component. Slot maps usually also have a free list, because slot maps should not, ideally not change. They should not shrink. You can shrink them, but that would invalidate handles, so be careful with that. But if you remove something from the slot map or make it invalid because this entity is erased, you would put it on the free list, increase the version number by 1. So whenever we erase an entity, we increase the version number by 1, put it on the free list. So that's a slot map. What about an archetype? An archetype is simply like a table-like organization of components. And in this case here, we collect all the entities that have exactly the same components, or maybe even the same tags. And then we have all the components for the enemies in this table, right one after the other. So in VECS, in my ECS, there's always a handle also stored here. That's nice because when you iterate through all the entities, you can also get the handle from your entity, and then you can operate on the entity. You can destroy it, you can delete it. You can add another component. So what happens when you add another component? That's the bad side. So let's say we have here this entity. We add another component. That means that I have to move it into different archetypes, because now the entity has these components and also the pink one. So it should be here. So I have to move it down here. Then I have a gap here. I have to close the gap. So I have to move the last one over the gap. And then I have to update the slot map. So that comes with an overhead. It's not. It's unfortunate that all of this has to be done, but it's kind of cache optimal. And yeah, let's do the same thing again. Solid lines are the random numbers, and dashed lines are now the sequential numbers. So these are the measurement values when you go through these synchronized segmented vectors. Then we see that there is indeed almost an order of magnitude better performance. So, consequences. Adding, erasing components or tags moves components to another archetype. That's the bad thing. As a consequence, we cannot use pointers or references. That's that's actually a bad idea. So either you don't use any references at all, but as a programmer, I like references actually. It's very convenient to use them. The solution in my ECS is that whenever you specify that you want a reference, you don't get a reference, you get a ref object. And the ref object actually will point to the slot map. The ref object will point here. So it's like a little bit of cheating, but because the slot map is always updated when the components are moved, then you never lose track of the entity and where it currently is. There's another thing that is also really, really annoying, and that's when you iterate over all the entities and you actually decide to delete one, or you move one because you add a component. And that means that, as we have seen, so let's say we iterate over all of them. We iterate, go here, 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 here. We decide to add a component here. It's moved out. The last one is moved here. And because we have our lazy iterator, we just go to the next step. But we'll never see this one, because it has been moved in here. So we're jumping over an entity, and we have to be aware of that can actually happen. So what can you do? You simply don't close the gap until you reach the end of the archetype. You simply collect all of these moved entities, you leave the gap, and when you reach the last, when you reach the end of the archetype, then you close the gaps. So I'm almost done. This is an example. This is how I implemented, well, the interface of my insert. It's of course it's a variadic template. You have a lot of types that you can have. Then I enforce, of course, there must be some type here. It shouldn't be an empty call. All the types have to be unique, so you can't have integer 2 times. And it shouldn't have a handle, because a handle is automatically created, and you shouldn't be allowed to have your own handle. So that should flag a compiler error. Then I get a new slot map index, and we will come to this later on. And I insert something into the slot map, and then I get a handle and a slot. Then I have to get my archetype. This is the storage, and then I can fill the slot here already with archetype, and then here I insert something in the archetype. I get the index back, and I store the index. Just for fun, because it's C++ here, the topic. How did I implement this? I used simply type lists. The first version of my ECS was actually completely compile time, and that means that I had to handle a lot of type lists, but it's very strict. Turned out it's not really well suited for game engines, so I dumped it. But what I did was I used a lot of type lists, and this is a type list. So here we have a template struct, we call it type list, and it's simply a variabic template. This can be simply completely empty. There's no need to put anything in here, and that's a type list. It's a struct that has variadic type, or a list of types. And by using that, you can come up with your own metaprogramming algorithms, and that's something I created for the first version, the compile time version. And this is my implementation for has type. So has type, how does it work? So we have this, the struct has type. We give it 2 things. We give it a sequence and a type. And the quest now is to store in the static const bool either true or false. Is the type in this type list or not? And in order to do that, I simply call something in my detail namespace. Here we have the primary template, which is simply a copy of that. And then I have 2 more templates that are more specific. One would be, I expect a sequence to be a type list itself. So that looks kind of intimidated, and took me a long time to figure that out, things like that. And then I'd simply specify that the sequence is empty. And when something is empty, the type cannot be in there. So we set the value to false. If it's not empty, then it has to be a sequence with types. So we do this here, this specification. We have these types, type lists and the type. And then we set the value to the result of this, this fold expression, which is fairly easy. We call simply is same. So we go through all of the types in this type list. Is it the same, yes or no? And then we make a big OR, and then we get the result. So this is the one thing. And the other one would be checking if the types are unique. It's pretty much a very similar idea. If it's an empty sequence, yes, then everything is unique because there's nothing there. Otherwise, what we have is a recursion. So the first one was a fold expression. This one is a recursion. I simply use has type. This is the function that I just defined before that. And I go through all of the... So I define the sequence to have a starting type and then the rest of the types. And then I simply check whether the rest of the type contains the starting type. And then if that's not the case, then I can go on and so on. So this is a recursion. So this is how you can do it. And I'm already over my time, so I will hand over to Mrs. Hölzl.
Thank you. So I had the honor to make my bachelor thesis about parallelizing the Vienna Entity Component System. My approach was a bit timid because I wanted to make as minimal changes to the original registry class as possible. I was a bit scared to mess everything up or some things, so I went for a modular approach, and also I wanted to obviously have a better performance since parallelization shouldn't be slower than the sequential version. I did this by making a manager class. It's basically a proxy class that manages the registry. So when we first initialize the manager class, it also gets a shared pointer to the registry, which was explained before as the world variable, and a thread pool. And to leverage multi-threading, I implemented specialized methods. So, for example, we saw how we would use the method view. I implemented one for each view. So what we can do with this is it's basically the same setup. You throw in some of the component types you want to have and you want to loop over it. And then you can, as a parameter, put in a lambda function, what you want to do for each of those entities with the components. And the same with the insert bulk. As of now, I only had the insert bulk to create a number of entities that are with their, what's the word? Default values. Yeah. And erase bulk just takes a vector of entity handles and goes over that to erase all of them. For the multi-threading for each view, I separated the entities according to their archetypes they belong to. And so you can, under the hood, say that every thread gets to iterate over an archetype. So it's split among the threads according to the archetypes the entities belong to. For locking, I made use of shared locks for reading access and scoped locks for writing access. I used the mutexes already presented for the registry, and I think the archetype mutex I implemented. I'm not sure if that was already there. Slot map mutex was also already implemented. But there weren't many slot maps, just one in the sequential version, and I changed it to use, I think, 16 slot maps for the parallel version. And yeah, so I should have maybe included some code examples, but I have done a lot of benchmarks. I think it's more, it makes more of an impression if you can see how the benchmarks how the benchmarks turned out. And there's also some of the entity component systems Professor Hlavacs already introduced, like the ENTT. It's the dark blue one, and this is, for example, benchmark testing, iterating over all entities with 2 different systems. So some having velocity in position and some others with inertia and some other components. For this, I used the for each view function and split the workload. So the light green one and the almost not noticeable very mint green are the VECS implementations. The darker one is the sequential version, and the very light one is the parallel one. And you can see that as the entities, as more entities are iterated over, the performance will get better compared to the sequential version. And it's the same benchmark, just with 7 systems. There is not much difference. I mean, you can see that it is from the 1 micro, like half of a microsecond, to 2-3 microseconds. But that's because there's 7 systems. And yeah, it's both with mixed components, so not just one, different components. And then also applying with those first 2, you always apply some kind of function. With those last 2 benchmarks, there is just iterating over the entities. So it's simple iteration. You don't touch any of the components except for reading them. And there are still a lot of places I want to improve the performance. I didn't include any of the accessing, so simply accessing and reading the values, because I have found some errors which I have to get to and fix. But in total, it turned out quite well, except for the overhead you have in the beginning for setting up the whole manager class thing. And not accessing the registry directly. And yeah, I think Mr. Hlavacs will tell you about the part of my colleague.
Thank you very much. There is another aspect. So our 3rd presenter, she cannot be here, Mrs. Kasper, also is doing her bachelor thesis, and her task was to create a graphical user interface, call it the debug console, that allows you to look into the ECS, because that's really important. If you debug your own project, you really want to know what's inside the ECS currently. And so she came up with this her solution, which is simply an external program that an ECS instance can connect to. So the program runs completely parallel to the program that is using the ECS, and then you can send data from the ECS. If it's in debug mode, you can send data from the ECS to this debug console, and the debug console will then allow you to take either snapshots or a live view. So in the it allows you to load or dump snapshots from file. You can connect to a specific ECS that's currently running. And when you connect, you can create snapshots, and then you have this tabular visualization of all the values inside of for the entities. You can see the archetypes, you can see the values, and then you have a live view also, where you actually see how many entities are currently. So the other thing is a snapshot. You click on it and then you get like a static copy. But this is a live view where you see over time how many entities do I have currently in my ECS, and you can also set some watch values when you want to watch whether component values actually change. We have been implementing this with ImGUI. You might see that, but we're using the ImGUI Docker, which is quite a nice thing, and that concludes my talk. So, as a conclusion, ECS are really a useful architectural pattern. They are widely used in the gaming industry. You can have many different architectural choices with performance impact. You have lots of optimization necessary to do that. Parallelization is difficult, but you can kind of do that, but it's very hard. Debugging is hard, and it requires some useful tools. You can use an LLM to create your own one, and I just wanted to conclude my talk. Create a C++ ECS with templates, archetypes, and segmented. Let's see what's happening. And it goes on. And it goes on, and it goes on. But I'm pretty sure that works. And it's not bad. So, but you have to test it. So it's a lot of code that is churned out, if you are that specific. Thank you for your attention. And it goes on.
So, thank you very much, and we have still some time for questions.
So, does the debugger also show the timing information, or is that not included because the overhead of you doing debugging is too high?
Yeah, so the debugger is just you can visualize a snapshot at a specific time. I'm not sure whether the time is actually also shown, but here I have a video that actually shows you how it works. So here we connect to an instance, we take a snapshot, and that actually get new snapshot, buff, so it's there. So that's actually pretty fast, surprisingly fast. So, and then we can scroll through all the entities and different archetypes, look into them, have values, see the values. And if I jump ahead, we can have a live view. And so she's starting the live view, and then entities are created all the time. They are put into the ECS. ECS will report the number of entities. And you can have your watch list down here where you can watch the stuff. What's nice about this ImGUI Docker version is that you can combine these very easily. So you have just moved them together, and then they're combined into one big window, and that's very nice for the if you use ImGUI. But I hope this answered your question.
Thank you.
Okay, any other questions? So then a question from my side. What makes Flex so much faster? What is their secret? What makes Flex so much faster?
Well, they have a lot of low detail optimization, like graphs and bit fields, and so they are super optimized. This is something that we still have to do. So that's I use too much SDL. I admit. Okay, because it had to work at some time. I don't have infinite time, so I cut corners.
Okay, so yeah, SDL isn't known for being cache friendly.
Absolutely,
I know about that. Yeah.
Not cache friendly, and you have all of these allocations in memory if you use it and things like that, which are not necessary. You can pre-allocate stuff and then work on that. For instance, that would be an optimization. Not use a vector because you have to allocate some memory and then fill it, but have some kind of pre-allocated arena where you can just snap something.
Mm-hmm. Okay, he was first.
Do you have experience with Stud Hive, which is not yet in the standard, but maybe...
That's a Hive, yes. There is actually a slide here. If you allow gaps, you might have colonies or hives. Yes. Okay. So there is a GitHub from the guy who invented that. You can test it out. And they use skip fields in order to, like, if you have a gap, then you have information to jump over the gap, and that's very feasible. So there's a good implementation for that. Now let's have a look at. But hives are definitely here it is. Okay. Yeah, so if you have gaps in an array, you allow for that, then you're not moving anything, but then you have to mark it as a gap. There's nothing here to see. And then you have your skip field that tells you to jump over that. Now, of course, when you jump over something enough, the access pattern is not predictable, so therefore you probably have a cache miss coming up. Otherwise, it's pretty good.
As far as I know, Hanna Tuskikova's most beloved data structure are the hives, and she's giving actually a talk in Brno in a couple of days, so who is interested might go there.
So I think it was heavily discussed whether it will be in the standard or not, right? In the 26 standard.
Yeah. Okay, we got time for last short question. If not, let's give them another applause and thank you very much for being here today.
Thanks for having me.